Thanks for having me today. I'd like to talk about using evidence factors in observational studies, and I'll say what I mean by that in a moment. The talk is built around a book which includes also an associated R package called Evident. So you could, if you'd like, reproduce analyses in the book and in the talk using that R package. These are some related references extending back over about a dozen years. This is a fairly non-technical talk about how to use evidence factors. If you'd like a talk about the theory of evidence factors, there are two links to such YouTube talks on my personal webpage. I want to start with two familiar facts and a question about them. The first fact is association does not imply causation. Treatment received and outcome exhibited may be associated in the absence of any effect caused by the treatment. In statistical terms, in the absence of random assignment of treatments, causal effects are not identified by observed associations. The same observable data, the same observable distributions are compatible with both a causal effect or with biased treatment assignment, or with some combination of the two. The second fact is that smoking causes lung cancer, and we know this. In fact, we know this as well as we know anything. And yet we know this mostly on the basis of the very sorts of associations that are seen in non-randomized observational studies that do not imply causation. So the question is, how can fact one and fact two both be true? They sound contradictory. This is a talk in two parts. The first part is review of various topics, one of which is replication in observational studies is not repetition of the same study. That's not a new idea, and it's certainly not original to me, so I'm going to try to keep that discussion fairly brief, but it's essential background for the new material in the second part. For those of you at Bristol, this may be very familiar ground. There's an excellent paper by Debbie Lawler, Kate Tilling, and George Davies Smith about triangulation in epidemiology. And that's very much related to this idea that replication is not repetition. There's also a very nice paper by Jack Bowden and colleagues about trying to achieve triangulation within a single study, and that's very closely related to the topic of evidence factors. The new part of the talk is about the technology of evidence factors, in which I'm going to ask, can an observational study replicate itself? Can an observational study provide two comparisons subject to different biases that may be combined as if they came from unrelated studies, one done in the UK by one investigative team on one group of people, another done in Australia by a different investigative team on a different group of people? Can one study have two analyses that are combined as if from different unrelated studies using meta-analytic techniques, so the combined comparison is insensitive to larger unmeasured biases? So that's the main question in the second part of the talk. There's a little bit more detail about the structure of the talk, so there'll be some background, as I say, about replication is not repetition. I'll briefly remind you about randomized experiments. There's a little bit of a review of sensitivity analysis in observational studies. Then we're going to look at two simple cases of randomized experiments with two evidence factors. They're just conceptual and very simple cases. And then we'll look at two observational studies which resemble those experiments in structure, but actually are potentially open to biases of various sorts. So replication is not repetition. In the 1980s and 1990s in the US, there were a number of big studies done to evaluate whether people who had been clinically treated for addiction to heroin or cocaine benefited from clinical treatments. This is often cited as replicated evidence of treatment effectiveness. So this is from one of the later studies. Hubbard et al. Wrote, the general finding from DARP and TOPS that treatment duration of at least 3 months is associated with statistically and clinically more positive outcomes supports the inference of treatment effectiveness. The following analysis retests this hypothesis using Dato's different data system, reaching the same conclusion. What should we make of the fact that a similar association was seen in 3 observational studies of similar design? In 1999 and 2001, the US National Academy of Sciences published 2 reports which did a number of things, but one of the things is they assessed whether the conclusions of these studies were warranted on the basis of the evidence from those studies. So I do want to emphasize that they're asking about whether the conclusions were justified by the evidence. They're not actually asking whether the conclusions are true or not, which might involve other evidence as well. Concerning treatment effects, Mansky, who was chair of the committee, and the committee itself wrote, the RAND study compares the post-treatment average drug use of members of the top sample who completed their treatment programs with drug use of top subjects who began treatment but dropped out within 3 months. Suppose, however, that treatment dropouts are more predisposed to drug use than those who complete the treatment. If dropouts are more severely addicted or less motivated or have fewer social supports than those who complete treatment, the observed differences in post-treatment drug use of dropouts and completers may reflect the differences in the characteristics of these 2 groups, not any effect of the treatment program. They continued, the people who complete their treatment program may be those who are more likely to reduce their drug use whether or not they receive treatment. The true treatment effect may be smaller than estimated by RAND, or even 0. So this is where we started, right? That the comparison is ambiguous. The same observable distributions are compatible with a treatment effect or with a bias. In this case, the most plausible treatment effect, that clinical treatment is actually beneficial, produces the same pattern as the most plausible bias, namely that people who are going to stay in treatment are the ones most committed to ending their addictions, and they might do better even in the absence of a treatment effect. So this is what I just said. Finding the same association 3 times is of very limited value if the same ambiguity keeps recurring. So how does an empirical association demonstrate a causal effect if that association is compatible with either an effect or a bias? How do you prove that what you're looking at is an effect and not a bias? So I'm going to turn to 2 philosophers for a bit of help with that question. The first is Wittgenstein. He said that a picture held us captive and we could not get outside it, for it lay in our language, and our language seemed to repeat it to us inexorably. What is the picture? The picture is the picture in the language in which the question was initially phrased. It's the picture that observed associations produce demonstrated conclusions, as in a deduction or a proof. It's the picture which suggests that an observational study has a very clear meaning on the day it's published in a scientific journal, and that its meaning isn't evolving as further evidence is collected. How do philosophers break free of a picture? They do so by offering alternative pictures. The alternative pictures are not intended as a substitute for the initial picture. They're rather just intended to allow us to break free from the initial picture and think about it in a variety of other ways. A philosopher of logic, Susan Hauck, suggested a very different picture in her book, Evidence and Inquiry. That was the picture of a crossword puzzle. So I'm going to express Hauck's idea in statistical terminology. She uses certain words that are heavily overburdened, like independent, in ways that are incompatible with statistical terminology. So I'm going to use conventional statistical terminology to re-express what are her ideas. Her first thought is that the crossword entries are informed by, but not identified by, the individual clues. So for example, 16 across over here is German wheels in 4 letters. That turns out to be an Audi, but it could just as easily have been an Opel, another German car manufacturer. No amount of staring at that clue and that empty space would resolve the matter. So the clue is helpful, but it doesn't identify the answer. 1 across is Desert Storm Missile in 4 letters. What is it? Well, we might guess that it's a Scud missile. 1 down is Cry Noisily in 3 letters, perhaps beginning with S. 4 down is hound. We're not sure yet whether it's the animal or the activity in 3 letters, perhaps beginning with D, right? 17 across is an optimistic viewpoint to look upon in 10 letters. So we might guess that to cry noisily is to sob, to hound is a dog, and the optimistic viewpoint to look upon is the bright side. So her first point is that a lot of the reason we believe that an entry is filled incorrectly is not just from the direct evidence from the clues, but also from its appropriate intersection with other items, its coherence with the rest of the filling in of the puzzle. Coherence, as she says, lacks sharp boundaries. Brightside does not intersect with Scud, yet Brightside provides quite a bit of support for Scud because it supports Sob and Dog, which do have direct intersections with Scud. So the filling in of parts of the puzzle that are remote from a particular entry may actually support that entry because of the lack of sharp boundaries between incoherence. The reasoning here is circular, but not viciously circular. So vicious circularity would be if I said A implies B, B implies A, therefore A and B are both true. That would simply be an error in logic, right? It's true A supports B and B supports A, but it's perfectly compatible with A and B both being false. The sense in which this is not vicious circularity is that we may look at the evidence we have for, say, Sob that doesn't come from its appropriate intersection with Scud. We may look at the evidence for Scud that doesn't come from its appropriate intersection with Sob. So what evidence do we have for Sob besides its appropriate intersection with Scud? We have the fact that it fits the clue, it meets Brightside appropriately, and Brightside meets Dog appropriately. So we have a lot of reason to believe in Sob that doesn't come from Scud. In the same way, there's a lot of reason to think that Scud is correct apart from its intersection with Sob. So now we have 2 things which we have reason to believe, and they meet appropriately, and that provides a useful confirmation of that wasn't available earlier and that was missing from vicious circularity. The identification that is missing in a crossword puzzle seems to diminish as more and more of the crossword puzzle is filled in, but it is never entirely eliminated, right? So it seems to diminish to the point of irrelevance, as perhaps the lack of identification of the smoking and lung cancer effect diminishes to the point of irrelevance, but it's never completely gone, right? You could imagine having a crossword puzzle which could be filled in 2 completely incompatible ways, and yet both would fit the clues, right? In one, 16 across would be Opal, and one 16 across would be Audi. Yet the possibility of doing that seems remote, particularly if someone didn't try to construct such a thing to begin with. One last comment from our philosophers. Wittgenstein said light dawns gradually over the whole, and that's certainly how a crossword puzzle is filled in, and also I think how evidence about, say, smoking and lung cancer accumulates. Let me give a one-slide example of a replication that's not a repetition. In the 1950s and 1960s, many studies found strong associations between smoking and lung cancer. They also found weaker associations, some of which are thought nowadays to be causal and others thought to be spurious. In the 1960s, there was a very active campaign by the tobacco producers to promote smoking among women. Women were not smoking very much at that time. The most famous of these campaigns, or notorious of these campaigns, was the Virginia Slims campaign with the slogan, "You've come a long way, baby," which suggested that glamorous, slender, independent-minded women would, of course, smoke. About 30 years later, about the right amount of time for lung cancer, Baylor and Gornick wrote in the New England Journal, for lung cancer, death rates for women 55 and older have increased to almost 4 times the 1970 rate, but rates for males over 55 and rates for other cancer sites show no such dramatic change. So this is a second entry in the crossword puzzle, right? It's very different from the first entry. What's wrong with the first entry doesn't seem to have a lot to do with what's wrong with the second. Even better, the most common complaint about the first entry is that it could be that there was a gene which had an adverse effect on people's lungs and making it attractive for people to smoke, and also led them to have lung cancer. But that doesn't really seem to explain what we see with the Virginia Slims campaign. In order to postulate a genetic reason for the increase in lung cancer among women, you'd have to postulate a lot of rapid evolution among women and an evolution that's not shared with men. So it would be seen to be a fairly remote possibility. That's true despite the fact that the second piece of evidence is not a very good piece of evidence, right? It's just a demographic trend, but it weakens the most logical complaint about the first kind of evidence. So replication is not repetition. If we can't eliminate a bias, perhaps we can change it to see if the treatment effect persists when the biases are changed. This raises a key question. If replication is neither about doing the same study twice, nor about increasing the sample size, then ask, can one observational study replicate itself? Can one observational study conduct two inconclusive analyses subject to different biases in such a way that the evidence against bias and in favor of a treatment effect becomes quantitatively, measurably stronger? Let me briefly remind you about randomized experiments. To understand observational studies, we need to understand randomized experiments. Fisher, the inventor of randomized experimentation, spoke of randomization as the reasoned basis for inference in experiments, as the physical basis for the validity of the test. He wrote extensively about that. What did he mean? I'm going to use Fisher's numerical example, which is a tiny, very dramatic example intended for illustration. But I'm not going to use his narrative around this example. I'm going to use a more traditional clinical narrative surrounding this example. So we have 8 people. That's part of what makes this very simple. It's very small sample size. We can see everything happening. And we're looking at survival to 30 days after treatment. And 1 indicates survival, 0 indicates death within 30 days. And you see that person 1 survived, person 2 did not, and so forth. What's the null hypothesis of no treatment effect? The null hypothesis of no treatment effect says if I change the treatments people got, I wouldn't change who lives and who dies. Some people live, some people die, but if I changed what treatment they got, their survival to 30 days would not change. That's what the hypothesis says. Might be true, might be false. What is a randomized experiment? We flip a fair coin independently, repeatedly, assigning people to treatment or control until we've gotten 4 in one group and put the remainder in the other group. As it turns out, this is the treatment assignment we got by coin flips. The treatment a person receives is unrelated to every attribute of the person in the sense that the coin didn't care about those attributes and just fell in a fair and random way. I didn't say person 2 looks like a good candidate for treatment, or why don't you guys pick your own treatments? I didn't do things like that. I had a really random device that assigned treatments. There are 8 choose 4 or 70 ways to pick 4 people of 8 people to get the treatment. And in a randomized experiment, we know the probability of each of those ways of assigning treatments is 1/70th or 0.0143. So by definition, the treatment has no effect if changing the treatment a person receives does not change whether they survive. What we see here in this particular example is that every treated person survived and every control did not. Again, this is for a tiny example that you can see everything on one slide. So we saw a perfect match between survival and treatment. Could it be luck that we saw this perfect match? Well, it could be luck, right? The coins could have fell in just this way, even though the treatment is not affecting who survives. But we actually know exactly the probability that it's luck because we created that probability in randomizing. We know that there's only one way you get perfect match, and that one way occurs from coin flips only one time in 70 by chance. So the p-value testing the null hypothesis of no treatment effect is 0.0143. Only one time in 70 would you accidentally see this table if in fact the treatment had no effect. Fisher makes two important observations about this, A and B. A is the conclusion we just reached depended on the fact that we randomly assigned treatments, and it depended on nothing else. There's no assumption that there are no unmeasured confounders. There's no model for who lives and who dies. It depends on the fact that we randomized, and we did randomize, so we are entitled to this inference. The second point he makes is that the argument does depend on random assignment of treatment, and it falls apart without random assignment of treatment. Without randomized treatment assignment, you're immediately into arguments with strangers about unmeasured confounders, arguments that may be hard to bring to a rapid closure. I want to mention sensitivity to unmeasured bias because we're going to use that in the second part of the talk. It's the last piece of the review. Sensitivity analyses exist in a variety of forms, but the one that's oldest and most familiar, I think, to epidemiologists is the one from the paper by Kornfield and colleagues in 1959, reviewing the literature on smoking and lung cancer. So I'm going to talk over these. You can read them if you'd like. But essentially what they said is that it's true that association does not imply causation, but in order to explain what we saw in the analysis, to explain the pattern we see, the bias has to be a particular magnitude. So this is an enormous conceptual advance. It's a big step beyond association does not imply causation. It says that to explain the association you actually saw, the biases have to be of a certain magnitude. No longer could a critic say, well, anything can explain everything, right? The biases that are needed to explain a particular association that you saw have to meet certain standards in order to be logically coherent. Kornfield's method was sort of an add-on. It's in the appendix to this paper, and it was kind of a back-of-the-envelope argument. And it's an enormously important conceptual advance, but as a practical tool, it has some limitations. It ignores sampling variability. It pretends every estimate is the true population quantity. So it can report that the most insensitive conclusions come from the smallest and most unstable studies, just simply because the estimate is erratic and extreme. Saying the same thing in a different way, we really want to talk about the sensitivity of our inferences, our p-values, our confidence intervals, our estimates on multiple inference procedures, the things we can see, how sensitive they are to unmeasured biases, not talking about population quantities to which we have no direct access. The method is tied to binary responses and doesn't have an obvious extension to other common situations. It doesn't naturally incorporate adjustments for observed covariates, though they are a standard part of inference and observational studies. But if you make small edits in their method, you can produce a method which is very similar in spirit to their method and fixes these various issues. Let's take an example. So this is Hammond's study of smoking and lung cancer in 1964. He compared men who smoke regularly, who never smoke regularly, to men who smoke 20 or more cigarettes a day at enrollment. It was a prospective study. Men were matched for baseline and followed for 34 months. They were matched for a variety of things. They produced 36,975 smoker control match pairs. They used the McNamara-Cox test, which is the uniformly most powerful unbiased test. So this led them to focus on discordant pairs, pairs in which one person, either the smoker or control, died of lung cancer and the other did not. And they did a variety of things to ensure the quality of their data. The sensitivity model says two individuals matched for certain observed covariates may differ in their odds of being the smoker in the pair by at most a factor of gamma. So gamma equals 1 gives you exactly Fisher's randomization inferences. Gamma greater than 1 means we don't really know the distribution of treatment assignments, but it constrains how far we are from the randomization distribution. We vary gamma to permit larger or smaller departures from random assignment. The causal inference is uncertain when gamma is greater than 1, so one obtains not a p-value, but an interval of p-values, not a point estimate, but an interval of point estimates, not an endpoint for a confidence interval, but an interval of endpoints for a confidence interval. The question is, how far from randomization would you have to go for the interval to constitute a qualitative change in the study's conclusions. You reject the hypothesis and you don't accept it for different points in the interval. The endpoint of the confidence interval could be strictly above 0 or extend below 0, things of that sort. In a paired randomized experiment, we flip a fair coin once for each pair to assign treatments, and everybody has probability 1/2 of being the treated person in their pair. What does gamma equal to 2 mean? Gamma equal to 2 means that the chance that the first person in the pair is treated could be as low as 1/3 or as high as 2/3. That's a big departure from 1/2, or this is the general formula for what gamma means. Sometimes we prefer not to talk about departure from a randomized experiment, but about how strongly an unobserved covariate is associated with the treatment and the outcome. For example, gamma equal to 2 is exactly the same as an unobserved covariate that increases the odds of treatment in a pair by a factor of 3 and increases the odds of the less favorable outcome in the pair, in this case lung cancer, by a factor of 5. And this is the general formula for that re-expression. In fact, there were 122 discordant pairs where one person died of lung cancer and the other did not in this collection. The split was 12 of the non-smokers died of lung cancer and 110 of the smokers died of lung cancer in discordant pairs. If this had been a randomized experiment, then the p-value testing no treatment effect would have been on the order of 10 to the minus 21st. And we would be 95% confident that smoking causes at least 80% of the 110 lung cancers among smokers. If gamma is 2, that's a big departure from a randomized experiment, but the maximum possible p-value testing no effect we could get is 10 to the minus 9th, and we would still be 95% confident that smoking caused at least 62% of the 110 lung cancers among smokers. So you remember that gamma equal to 2 is an unobserved covariate that triples the odds of smoking and increases the odds of lung cancer 5-fold. So it's not a trivial unobserved covariate. At gamma equal to 5, the p-value for no effect would just be about to cross the conventional 0.05 level. There would be some p-values above and some below 0.05. The maximum p-value at this point is 0.02, so it's getting very close. And we are 95% confident that smoking caused at least 9% of the 110 lung cancers. Gamma equal to 5 is a very big bias. It's an unobserved covariate that increases the odds of smoking 9-fold and increases the odds of lung cancer 11-fold. So that's a major omission from a study. So now I want to shift to the main topic of the talk, which is about evidence factors. I'm going to start by thinking about 2 randomized experiments, each of which have 2 evidence factors. Then we're going to think about analogous observational studies with the same structure. So imagine the simplest of studies, which would have 3 treatment groups, A, B, and C. We roll a die. If you get a 1 or a 2, you go to A. If you get a 3 or a 4, you go to B. If you get a 5 or a 6, you go to C. Every person has a 1/3 chance of receiving each of the 3 treatments. Let's think about a different experiment. In this experiment, we have A versus L as treatments. I roll a die and 1 or 2 gives you A and 3 through 6 gives you L. But L is the lottery treatment, which involves flipping a coin to assign you to either B or to treatment C. So there's a die roll followed by a coin flip. Of course, in one sense, these are exactly the same, right? Ultimately, everyone has the same probability, 1/3, of receiving each of the 3 treatments. But in another sense, the A versus L comparison is, in a sense I will describe, almost independent of the B versus C comparison. It's almost as if they came from different studies. In certain specific ways, we can act as if the A versus L comparison was one group of people done by one group of investigators, and the B versus C comparison is from an unrelated study of different people by different investigators, and combine them using meta-analytic techniques to provide either mutual support or contradiction. We have conflicting intuitions about whether this is true. The A versus L comparison, I said, is almost independent of the B versus C comparison. One intuition is if I told you that B was more effective than C, it wouldn't help you to figure out whether A is more effective than L, right? So that's a sense in which they feel like they're disconnecting as comparisons. On the other hand, if we had a particular person, say Harry, and he was an unusual person with an unusual outcome, and he was assigned to treatment group A, then I know that he's not in treatment groups B versus C, and not in the lottery, and not in either group B or in group C. So that sounds very dependent, right? If I know something about a person in one group, I know they're not in another group. It seems like that must be some kind of serious dependence. Mostly when I analyze the same data twice, I merely repeat myself, right? And if I think I'm confirming my findings by analyzing the same data in similar ways twice, I'm just kidding myself, right? But that's not true of the A versus L and the B versus C analyses. They are different for structural reasons that we'll think about. It's actually much better in observational studies because the A versus L comparison may be affected by certain biases that don't affect the B versus C comparison. And the B versus C comparison may be affected by certain biases that don't affect the A versus L comparison. So the meta-analysis may be insensitive to larger biases than each of its components. And we'll see how that happens. Here's a second randomized experiment with a different structure, but also with two evidence factors. So the treatment condition has a dose, but the control condition does not have a dose. There are two I individuals where I is some number, and they're in I pairs. They've been matched to be similar on covariates. One person in the pair is picked at random for treatment, the other receiving control. Then we randomize the doses and assign them to the pairs. So some pairs get big doses and some pairs get small doses. One factor ignores the doses and compares treated and control. The second factor fixes treated versus control and takes the treated minus control difference in outcomes and asks whether that's predicted by the doses within the pairs. Again, in certain specific analyses, this is almost the same as having two unrelated studies that we can combine using meta-analytic techniques. So now I want to turn to some very simple examples of observational studies with this same structure. So I'm picking very simple examples because evidence factors tend to appear near the end, and I want to get to the end where the evidence factors arise fairly quickly. But these same issues would arise in more complicated studies. They just arise with more preamble. So this is a study of that appeared in Mutagenesis in 2001, and it was concerned with whether the people who administer cancer chemotherapies, doctors and nurses who administer cancer chemotherapies, are being injured by that, whether those cancer chemotherapies are damaging their DNA. DNA damage was assessed by the comet tail assay applied to a blood sample. So the standard assay for genetic damage. So you can read the bottom if you want the technical bits, but the comet tail assay, you take blood out from a blood sample, you take out certain types of cells, you take the DNA out of the cells, and you put it in an electric field. DNA is a big molecule. The electric field is not very strong. It doesn't move intact pieces of DNA very much, and they remain over here in the head of the comet. But broken pieces of DNA are pulled by the electric field and form the image of a comet with a tail. The size of the tail and the amount of material in the tail is taken as an indication of genetic damage. Large values of the comet tail assay are taken to signify more DNA damage. The study had 20 controls. These were healthy students or office workers. The exposed group were nurses and doctors in daily or almost daily contact with anti-neoplastic drugs. It's a fairly standard list of such drugs. The exposed group was divided again. So 20 of the people who were exposed were protected by latex gloves. 19 people were both protected by latex gloves and also a biological safety cabinet with vertical airflow, which kept some of the fumes away from them. Factor 1 is exposed versus control. Factor 2 is gloves versus hood referring to the biological safety cabinet. So this is somebody working with one of those biological safety cabinets. There's no obvious reason why the biases in these two comparisons should align. Either comparison could be biased, but they seem to be affected by different biases. Factor one is affected by everything that distinguishes nurses and doctors from students and office workers. In particular, factor one is biased by everything that happens in hospitals, right? The doctors and nurses are in the hospital all the time. So there's radiation in use in hospitals. There are other drugs and chemicals and cleaning agents in use in hospitals. And there are also a wide variety of unusual viruses and bacteria that you don't often encounter wandering the streets. There's also potential for bias in who becomes a doctor or a nurse versus who becomes a student or an office worker. Factor two is not biased in these ways because everyone is a doctor or a nurse in a hospital, but it is biased by whatever leads some hospitals to provide better safety equipment for their employees than others. And perhaps they do that in multiple ways, not just this biological safety cabinet. Maybe they take better care, caution about radiation or other drugs or chemicals. This is the comparison. So this is the three-group comparison. The tail moment of the common assay, higher values indicating more genetic damage. So you see the gloves group at the highest level, the hood group was in the middle, and the control group was the lowest. This is factor one, control versus exposed. This is factor two, just focusing on the exposed and looking at the people with or without the biological safety cabinet. So you're getting the predictions you would have thought would have happened in this case, right? That the exposed group has more damage than the control group, and people who are protected by the biological safety cabinet seem to have less genetic damage than people who are not. So there's an old fact, it goes back really to the 1930s paper by Renyi in Hungarian, which is very hard to come by. But an easy paper to locate is the paper by Alam and Jaza in 1974. That's in JSTOR. And this fact talks about Wilcoxon's rank sum statistic effectively. So what would applying Wilcoxon's rank sum statistic mean for factor one? We have 59 people. We would rank their comet tail assay results from 1 to 59, 59 being the largest and 1 being the smallest, and we would sum the ranks in one of the groups, say in the exposed group. That would give us Wilcoxon's rank sum statistic for factor one. Then we might do the same thing for factor two. We would take the 39 people in factor two, rank their comet assay scores from 1 to 39, and sum the ranks in, say, the gloves group. That would give us 2 Wilcoxon statistics. An old fact is that in a randomized experiment with no treatment effect, those 2 Wilcoxon statistics are exactly independent of one another. It is exactly as if they came from independent studies of different people. So it's in effect saying instead of having 59 people or 39 people, we have 59 plus 39 people or 98 people, even though we really only have 59 people. So this reanalysis of the same data is actually as if we're getting extra data. And there has been some discussion of how you might combine results from the 2 comparisons using meta-analytic techniques. All of this is not strictly true if I change the test statistic and it's not a ranked test, and it's not strictly true if I'm not talking only about randomized experiments, but also trying to do sensitivity analyses. But if you're a bit careful, you can find that everything we need is present, not just for rank sum statistics, but for many statistics, and we can do the sensitivity analyses as well in this context. If we use Wilcoxon's rank sum statistic and we do a sensitivity analysis, the first factor, this factor here, exposed versus control, is insensitive to enormous biases. A bias of gamma equal to 50, 10 times bigger than the smoking and lung cancer comparison, is still insensitive to bias. We would still reject the null hypothesis of no treatment effect in the presence of a bias of gamma equal to 50 for every possible bias of that magnitude. It has to be bigger than that, but it's about to become sensitive at gamma equal to 50. The second factor is pretty insensitive to bias. It's insensitive to bias of gamma equal to 3. That's this factor. So that's a fairly large bias. It's not as large as smoking and lung cancer, but it would easily blow away most of what's published in the American Journal of Epidemiology. If we do a meta-analysis to combine the 2 factors, putting them together into a single analysis, the result is much more insensitive to bias than each of the components. The joint analysis is insensitive to a bias in the first factor of 125, not 50, and in the second factor to gamma equal to 4, not 3. And that's still a significant difference. Moreover, we can demarcate the evidence, and we can say, what evidence would remain if we took away the first factor? We have fairly strong evidence if we took away the first factor. What if we took away the second factor? Well, we need to have very strong evidence if we had the first factor and not the second. So even infinite biases affecting one of the factors wouldn't invalidate the overall conclusion. You would find similar results if you stratified by age, and I won't do that in this example. The second example is smoking and periodontal disease. And so this resembles the second randomized experiment. Does smoking cause periodontal disease? Yes, say Tomar and asthma in the Journal of Periodontal Disease. And so a number of years later, the Centers for Disease Control agreed with them. We're going to look at some data that's a little more recent than the data analyzed by Tomar and asthma. This is data from the 2011-2012 National Health and Nutrition Examination Survey. The outcome is a measure of periodontal disease. So for each of 28 teeth, they looked at 6 locations, or 28 times 6 locations, and they determined whether there was a loss of attachment of at least 4 millimeters or a pocket depth of at least 4 millimeters. So they're looking for separation of tooth and gum at 6 times 28 locations, and the outcome is the percent of those 6 times 28 locations that exhibit disease, 0 to 100%. We have 441 matched pairs of a daily smoker and a never smoker. So smokers smoked every day for the past 30 days, whereas never smokers smoked fewer than 100 cigarettes in their lives. So these are real smokers and real non-smokers. Daily smokers began smoking 30 years ago on average, and 90% had been smoking for more than 14.9 years. Pairs were matched for age, gender, 5 categories of education, income, and Black race. So it's easy to think of other things that you might like to match for. We're also going to take note of the number of cigarettes smoked by the smoker in each pair. So this is the first factor. This is just looking at smoker versus control, the difference between the smoker level of periodontal disease and the non-smoker. So it goes from minus 100% to 100%, whereas the values for one person go from 0 to 100%. Positive values mean the smoker had more periodontal disease than the non-smoker. Negative values indicate that the non-smoker had more periodontal disease. The value right here is 0, right? So most of the box plot is to the right of 0. Usually the smoker had more periodontal disease than the non-smoker, but there are individual exceptions where the non-smoker had more periodontal disease than the smoker. If we did Wilcoxon signed rank statistic, his other test statistic for matched pairs, which is another randomization test, we would get a very small p-value. Actually, I quoted it as 1 in 10,000, but it's actually below machine precision. So the machine just says it's 0, even though it's not 0, it's small. If we inverted Wilcoxon statistic to get a point estimate, the Hodges-Lehmann point estimate, we would find that it estimates a 13.5% increase in periodontal disease associated with smoking compared to controls, with a 95% confidence interval also obtained by inverting the test from 10% to 17%. So we're reasonably convinced that this is not chance, right? But it doesn't necessarily indicate an effect caused by the treatment. We're not entitled to these inferences because they are based on the assumption of random assignment, which didn't take place. People didn't randomly decide to become smokers or non-smokers. What other explanations are possible? Well, it could be that by smoking, a person is expressing a lack of concern for their health, or perhaps a lack of confidence in the advice of health professionals about what would be good behavior for their health. And perhaps smokers are expressing this in multiple ways, perhaps by not flossing their teeth, perhaps by not seeing the dentist regularly, and so forth. And perhaps all we're really seeing is that people who don't care for themselves don't floss their teeth and have more periodontal disease, which isn't necessarily an effect of smoking per se. A randomized experiment would flip a fair coin independently 441 times to assign one person in each pair to smoker or control. That would produce 2 to the 441 possible treatment assignments, each with probability 2 to the minus 441. When we compare smokers and controls, ignoring the amount smoked using Wilcoxon's statistic, and we get a very small p-value, we're saying less than one randomization in 10,000, really a negligible number of randomizations would produce such a large Wilcoxon statistic by accident. And that's also the way the confidence interval is developed. We're not entitled to any of these inferences because we didn't randomize. A bias of gamma equal to 1.25 is kind of the barrier between a small and a large bias. It's neither small nor large. Instead of being 50-50 chance of getting the treatment, the probability of treatment could be as low as 0.44 or as high as 0.56 for one person in the pair or the other. Gamma equal to 1.25 is equivalent to an unobserved covariate that doubles the odds of smoking and doubles the odds of a positive difference in periodontal disease. So that's not a giant bias, but it's not a negligible bias either. So it's, as I say, a kind of a barrier between small and large. At gamma equal to 1.25, the maximum possible p-value from Wilcoxon's statistic is 10 to the minus 16th. So a bias like that couldn't begin to explain what we saw. At gamma equal to 2.75, the maximum p-value is about to cross 0.05. It's very close. It isn't quite there yet. That's an unobserved covariate that increases the odds of smoking fivefold and increases the odds of a positive difference in periodontal disease fivefold. So that's a big bias, a big omission from the study. Not as big as smoking and lung cancer, but a big one. There is, however, a second comparison, and this comparison looks at the smoker minus control pair difference in periodontal disease in relation to the amount smoked by the smoker. Do we see a larger difference in periodontal disease in pairs where the smoker smoked more cigarettes per day? So an alternative study design would forget about who smokes and just focus on how much people smoke. Some people smoke zero. That's what Thoma and Asma did in their comparison. This is a picture of the data. So this is, again, the pair differences that we were looking at before. The smoker minus control pair differences 100% to minus 100%. But now they're being plotted for each pair against the amount smoked by the smoker in the pair. 0 cigarettes, 20 cigarettes, out to 80 cigarettes. The red line here is the low-S smooth of this picture. And what are you seeing? You're seeing that when the smoker smokes 1 cigarette per day, the red line is very close to 0. It's a little positive, but very close to 0. And it's gradually drifting away from 0 as the smoker is smoking more and more, right? So we are seeing a tendency for the smoker, for pairs in which the smoker smoked a lot, to exhibit a bigger difference between smoker and control in periodontal disease. This is that same picture. All the points are in exactly the same place, but some of the features of the plot have changed. The plot has been cut at the quintiles. So this is the 20% of most positive differences. So smoker has the biggest gap between the smoker and the control in periodontal disease. This is the biggest gap in the other direction, right? You notice that these are essentially the negative ones, the cases where the control actually had more periodontal disease than the smoker. So this is the top 20% on Y and the bottom 20% on Y. In the same way, this is the bottom 20% of amount smoked and the top 20% of amount smoked. What we're going to do is we're going to look at the odds ratio in the corner, which is a common thing to do in tabular summaries in epidemiology papers. People's eyes go to the high dose, low dose comparison and the high outcome, low outcome comparison. That odds ratio is 3.65. And that generates another randomization test. And the p-value from that randomization test is 0.0022. So if we'd randomly assigned doses to pairs, which we didn't, the chance of seeing an odds ratio as big as 3.65 for the corners is very small. Turns out this is a good statistic for sensitivity analyses because it tends to be fairly insensitive to bias when there's a big dose-response relationship. There are 441 factorial ways to permute the doses among the pairs, and in a randomized experiment, each of these would have probability 1 over 441 factorial. Saying the same thing in a different way, the odds of smoking dose D equal 5 cigarettes, D cigarettes per day versus D prime cigarettes per day, two numbers of cigarettes are the same for all pairs because it's just random who gets D and who gets D prime in this randomized experiment. The quoted p-value is saying about one randomization in 500 would produce a cross-cut statistic as large as the one we saw if there really was no effect of smoking on periodontal disease. Again, we're not entitled to this p-value because the doses were not randomly assigned. How sensitive is this comparison to unmeasured biases in the way doses were assigned to pairs? Suppose we said that the odds of dose D cigarettes per day versus D prime cigarettes per day, two doses, differs from pair to pair by at most a factor of gamma prime. So that gamma prime is 1 for a randomized experiment. The maximum possible p-value is just about to cross 0.05 at gamma prime equal to 1.6. So remember, 1.25 was the barrier between a small and a large, smallish versus a largest bias. So it's a little bit on the side of a larger bias that it's insensitive to. These are the two pictures we've been looking at, right? This was the Wilcoxon analysis. The box plot, did smokers have more periodontal disease than non-smokers? This is the cross-cut analysis of whether smoke pairs in which the smokers smoked more, we see a bigger difference in smoker versus control, differences in periodontal disease. So these are our two evidence factors. We're about to put them together. We again have conflicting intuitions about whether they're unrelated. If I showed you the box plot, you'd have a hard time guessing what the scatter plot looks like. There's not real information in the box plot about whether this picture is going up or down or it's just plain horizontal. The other hand, if I showed you the scatter plot, you could project all the points horizontally and get the box plot. So in one sense, this seems like they're unrelated, and in another sense, it seems like they're very related. Nonetheless, we will have what we need here. The goal is to combine two sensitivity analyses without adding any new assumptions. So in particular, we want to stay away from the assumption that the person most likely to smoke is not also the person most likely to smoke a lot. That may be true. It may be that the person most likely to smoke has some attributes that make them likely to smoke a lot if they do smoke. There's no assumption that that's not true. They can be arbitrarily related. The basic claim is that the two upper bounds on the two p-values may be combined as if they came from unrelated studies, the crosscut and the Wilcoxon p-values. This claim rests on the assumptions that underlie the separate analyses, but there's no additional assumption that's connecting the two parts. This is the basic claim stated a little bit more formally. If the hypothesis of no treatment effect were true, if the bias in smoker control were at most gamma, if the bias in dose assignments were at most gamma prime, then the pair of p-values, one for the assigned rank statistic, one for the crosscut statistic, is stochastically larger than the uniform distribution on the unit square, which is what we need to act as if these p-values were independent of one another. This is not saying that the p-values are independent of one another. What it is saying is that the worst case bound is the independence case. The independence case is the case that's generating the upper bounds on the p-value. It says no matter how you build the joint distribution, which might be very dependent, the hardest case is the independence case, and so we focus on that one. This is showing you an analysis that's a meta-analysis of the two pieces. So you remember the Wilcoxon analysis was looking at the box plot, and it was about to become sensitive at 2.75. The crosscut analysis, notice 2.75 is in italic. The crosscut analysis was about to become insensitive at 1.6, right? And inside this table, you're seeing p-values that combine the two analyses using meta-analytic techniques. And what do you see? You see that the combined analysis is insensitive to larger biases. A bias of gamma equal to 3, which would have invalidated the Wilcoxon analysis, or a bias of 1.8 for the crosscut analysis, those two combine to a p-value of 0.046. So the combined analysis is insensitive to gamma equal to 3, gamma prime equal to 1.8, even though that bias would have explained either component on its own. We also can demarcate the analysis and say, suppose the crosscut statistic had infinite bias. We still have fairly strong evidence from the Wilcoxon analysis. Suppose the Wilcoxon analysis had infinite bias. We still have moderately strong evidence from the cross-cut analysis. So we have strong evidence even if one of the comparisons is infinitely biased. Maybe we made a mistake. Maybe we shouldn't have been permuting doses of smoking across all people, all pairs. If you think about it, who smokes a great deal? The people who smoke most tend to be young men. Women tend to smoke less at all ages, and men tend to smoke less as they get older, and the health effects of smoking are starting to become apparent. So this is breaking apart the pairs into 4 groups. The pairs are now in the group who are female or male, and 55 or less or above 55. What do you notice? The cross-cut odds ratios are sometimes much bigger, right? For women under the age of 55, the odds ratio is not 3-ish, 4-ish, but 16-ish. For women over the age of 55, the odds ratio is not about 3.65, but rather infinite. For men over the age of 55, the odds ratio is now 4.1. So maybe we should have stratified the analysis. So a stratified analysis would give us 4 2-by-2 tables for the cross-cut analysis, which we would think of as a 2-by-2-by-4 table. And we could analyze that using, say, something analogous to the Mantel-Haenszel statistic. The Wilcoxon statistic was going to be, was becoming insensitive at gamma equal to 2.75, and it's not affected by the stratification because it ignored the doses. Alone, the crosscut statistic was sensitive at about gamma equal to 1.6. That's about where it was going to cross the 0.05 barrier. This is comparing the unstratified and the stratified crosscut analysis. So the stratified crosscut analysis is insensitive to a bias of gamma prime equal to 2, whereas that would have easily explained the unstratified crosscut analysis. However, a bias of gamma prime equal to 2.25 could just begin to explain also the stratified analysis. We can combine the stratified analysis with the Wilcoxon analysis, and we get this comparison over here. What do you see? You see that if the Wilcoxon statistic had a bias of gamma equal to 3, and the crosscut analysis had a bias of gamma prime equal to 2.25, that would have invalidated either test on its own, but the combined meta-analysis of those two is insensitive to a bias of gamma equal to 3 for Wilcoxon, gamma equal to 2.25 for the crosscut statistic. So the combined analysis, once again, is insensitive to larger biases than its components. How would you use evidence factors if you wanted to? The methods depend on certain symmetries in the study design and certain methods of analysis. And I've illustrated 2 such designs and 2 sets of analyses. There are actually many such situations. I have only shown you 2. If you wanted to apply existing theory, which is what most of us do when we're analyzing data, we don't invent new methods, we apply existing theory. A natural place to start would be to take some of the examples in the R package evident, rerun them using the help command in R, and understand how they work, and then apply the same methods to data sets with the same structure. And that's all discussed in section 2 of part 2 of the book. If you wanted to develop new study designs with evidence factors or use new methods to analyze those, then you need to get into the theory a bit more, and that's the topic of part 3 of the book. So part 3 is the theory, part 2 is really just about doing standard things in a standard way. Let me summarize. In observational studies, both biases and treatment effects can replicate across independent studies. So effective replication is not repetition of the study. If you can't remove an unmeasured bias, perhaps you can disrupt it to see if the treatment effect remains in place despite the fact that you've changed the biases. Viewed in this way, a single observational study can replicate itself, performing several independent analyses potentially affected by different biases. These can effectively increase the sample size, but also address biases to the extent that one factor is affected by biases and the other perhaps is affected by different biases. Evidence factors occur in certain structured designs when randomization analyses and their associated sensitivity analyses have a certain form. And we considered two forms: the three-group form, where one of the groups was a lottery between two of the groups. And we also considered the case where we had matched pairs of treatment control, but the doses varied among the pairs. But there are many such structures which have the relevant symmetries. From this structure, two separate sensitivity analyses may be combined using meta-analytic techniques as if they came from independent studies, even though they didn't, because the independence case is the worst case, providing the sensitivity bound, even though the joint distributions may actually be strongly dependent. The strongly dependent ones are easier to deal with than the dependent ones, the independent ones. The independent ones provide the sensitivity bounds. So let me close here, and I would be delighted to have your comments or questions.
That was great. Really
Thanks.
interesting talk. Are there questions? Questions in the room? And Neil's going to look to find online questions. So one question about the last example you worked through, the detailed example about periodontal disease. Do you think combining you're assuming that or hoping that these two analyses, either looking at smokers versus non-smokers or then dose response within smokers, aren't sharing biases? Do you think that you could add to that another approach, such as negative controls, as they're now called, which you've used? So, for example, in those data, if you had the birth weight of the people, it's impossible that their smoking influences their own birth weight. That you could then, look to use something like that as a test or a way of showing whether they actually are independent estimates.
Sure. So there would be many things one could do to look for biases that are different from evidence factors, and checking for unmeasured for unaffected outcomes would be a way of checking for unmeasured biases. You could use multiple control groups for a similar kind of a purpose, and so forth. Many of these don't produce the feature of two independent comparisons which can be combined. Some of them are more in the spirit of equivalence testing, where you're trying to affirm that there isn't something rather than to find something. And so some of the mechanics are a little bit different. I seem to be seeing my fixed face rather than my image. Have I done something wrong with the screen? Should I be doing something different to be visible?
I've just asked to start your video again. We'll see if see how the bandwidth goes. We have a question from Jack Bowden, who asks, do evidence factors provide a way of increasing the statistical power to test a causal hypothesis? Or is the main purpose to increase robustness or reduce type 1 error?
So they do increase power in the sense that in the example I gave with 59 people, the two comparisons actually had 59 plus 39 people. So in a sense, there was more sample size for the two comparisons than there was for one of them. And again, that had something to do with the fact that the two pieces were almost independent. So the reuse of the data was adding information. That's fine, except sample size doesn't usually solve our problems in observational studies. So we could have a very big sample size and still be very uncertain about what the causal effect is. So the wonderful thing about evidence factors, they also help us get conclusions that are insensitive to larger biases. And so that's not something we could get simply by increasing the sample size. As we increase the sample size, we approach a limit called the design sensitivity, which is the maximum, even if we had infinite samples from this particular source, and we can't get beyond that. But if we have two evidence factors, we actually can have results that are insensitive to larger biases than the components.
Okay, thank you. We've also got Sebastian Baumeister, who has a question. I'm going to see if I can allow him to talk. Sebastian, do you want to unmute yourself and ask away?
Oh, sorry, that was a mistake.
No worries.
That's your. My eyesight's too bad.
Okay, so we have another question from Yoav Ben Shlomo. The same confounder, i.e. health conscientiousness, will predict both smoking behaviors and dental care, so bias of binary comparison. But this is also true for a dose response delta, so that the less health conscious also smoke more and brush less. So the bias is the same, and combining them doesn't get us away from this. Unlikely the occupation and DNA damage example. In this case, the gloves versus hood exposure was not a function of the person of the hospital, and so this was not compounded by the person.
Right. So this is the natural thought that the two examples are very different, because in the first example, it's about career choice, and the second example versus about which hospitals did what. In the second example, it's the same person deciding either to smoke or not, and deciding how much to smoke. And so one has the feeling that in the second example, there aren't really two independent pieces. What's actually happening is that the independence is not that an assumption. It's actually that the worst combination of biases happens to come with two independent pieces in certain structures, like that structure. So even if these two structures were very much related, the two pieces we were looking at would have been statistically independent and allowed us to combine them as independent pieces. One might ask, well, maybe the biases are necessarily the same for the two comparisons, but it's actually probably not true. If you think about who smokes a lot and who smokes a little, and why do people smoke a lot or a little, some people kind of smoke as an appetite suppressant. And that's a possible way of smoking. They smoke 1 or 2 cigarettes a day, perhaps as an alternative to eating. And you saw people like that in the scatter plot. There are some people who smoke compulsively. So they're actually rather different in the nature of their smoking. And what we're finding is that the second piece of evidence, whatever it's telling us about that, is actually a separate piece of evidence also confirming it. And it didn't have to be that way. The first piece of evidence doesn't tell us how the second piece would come out, nor does the second piece tell us how the first piece would have come out.
Right, so potentially there's quite a nice analogy here with the genetics, right? So if you take your description of multiple experiments, multiple independent experiments, you could argue that each of the genetic mechanisms that somebody might be investigating may well be independent, may well be inherited independently. And that's where you get some robustness from examining multiple pathways you don't get with other approaches.
Right. I think in the case of using genes as instruments in Mendelian randomization, you would be closer to like the first comparison, where you might take a few genes that you would compare a high and a low group on a few genes, and then fix those genes and say, I'm going to stratify on those genes. And now I'm going to look at a second group of genes within those strata. And then I would take the combined strata from those two groups of genes and go on to a third stratification. That would produce this mathematical structure, which would allow you to combine the pieces. That would allow the genes to be dependent upon each other in various ways, and yet allow you to have independent pieces because you've conditioned on one layer of genetic information when you look at the next layer.
So thinking again about the, I mean, maybe it's just saying what you are saying, but if you think there's somehow, if you think there's a difference, you know, as is reasonable to suggest in things that influence the amount smoked if you're a smoker, then then you would expect, if you like, if you did a sort of regression in terms of amounts smoked, you'd expect there to be a discontinuity at naught, because the ones who actually smoke at all are different from those who don't smoke in a way that is different. If it's the same, then you might just expect them to come together more at the very
Yeah, so we saw a little bit of that in that picture. Let's see if I guess I'm not sharing right now, right?
Yeah.
Let me see. So how do I share again? I'm not seeing the Zoom controls. Where's that? Oops, I know where. So here we go.
Yeah.
Let me back to. So are you seeing this?
Yeah.
So this is the picture.
Yeah.
So in the picture, we do seem to see that at very low doses of smoking, there isn't a big difference between the smoker and the control in periodontal disease. I'm not sure that's a given, because we are looking, unfortunately, at current smoking, which happens to predict pretty well past smoking, but you could imagine somebody who's currently smoking not too much, but smoked a lot in the past and maybe had damaged their teeth in the past. But this seems to be the situation where the dose seems to be predictive of the difference, and it vanishes as you get to zero dose.
Yeah.
Was that your question?
Yeah. So that sort of analysis, when you've got these these two particular types of evidence, again, you can obviously do more looking at those data and maybe looking at falsification tests. So a sort of general question: how do you go, if you've got a sort of data set? How do you go about thinking about what evidence factors can you get out of the data, or is that?
So I think there's two kinds of aspects here. So one is the kind that you were writing about in your triangulation papers, which is trying to find the scientific comparisons that would be of interest in providing mutually supportive pieces of evidence. And that's a very important part of it. The other part of it is to get the mathematical structure that allows these two pieces to be independent pieces that we could combine as if they came from different studies, and thereby make the combined analysis stronger. Those two pieces sort of need some pulling together of the science and the mathematics, because the mathematics is sort of devoid from the science. It says whatever this is, it has a certain mathematical property. It has to be pulled into a context where we actually have two evidence factors that seem interesting to us as a scientific setting. The basic thing to making this happen in a particular study is to have a design which has a certain symmetry to it. So the two designs I gave you had that kind of a symmetry to it, where what happened in one part of the design really didn't well predict what happened in the other. That's the mathematical structure of it. And then you need an interesting set of comparisons of which is scientifically interesting, because one could create something where they're not scientifically interesting, and yet they have the mathematical structure. Or one could have something that's scientifically interesting and not have the mathematical structure. The task is to sort of pull them together so you can do analyses which actually combine the two factors and quantitatively say, yes, I actually accomplished something. Yes, in fact, the combined analysis is stronger than the component analyses.
Deborah, do you want to come forward and or do you want to shout or come forward?
I'll shout.
Okay.
I'm still struggling with it a lot, particularly the smoking example. And I wondered to begin with, I suppose a bit like George was saying, how similar this is to Eric Chepton's idea that instead of in triangulation bringing different sources of evidence, potentially from very different studies, doing it all in the one study. Now, his rationale for doing that seems quite different to yours, which is if you do it all in one study, for example, UK Biobank, but you do Mendelian randomization, negative controls, conventional multivariable regression, within that one study, you reduce the other extraneous things that might make your results differ between different studies. He's not doing it in order to make these like independent studies so that you can meta-analyze them. I think that's what you're saying. What I'm struggling with is how you can have the same study and say that they're independent and therefore can meta-analyze them. And I guess, again, just repeating what Yov says, how does that help if the two things you're meta-analyzing are biased anyhow?
Well,
isn't
it exactly? But it's exactly like we meta-analyze multiple SNPs, right?
Yeah,
so if you're
exactly.
using an IEW estimate, you can meta-analyze two SNPs together because they're independent.
Because they're,
and
you're doing it all the time.
Yeah, but we have to. But I'm struggling with this. I guess it's the same.
So
let me try. What I was hearing from two of the questions, yours and one of the previous ones, was that you liked the first example better than the second. Is that right? That in the first one, it seemed that the...
Yeah, I can grasp the first example, but not the second.
Okay. So I think that the issue is that both examples have the same underlying mathematical structure, and that structure snaps into place in many different scientific contexts. How much you like the scientific context might vary because of the scientific context. And so one might like the first example for its scientific context better than the second, but the second example also has the same relevant mathematical structure. So I've tried to sell the second example as having reasonable scientific structure as well by saying that, people smoke for different reasons. And this person out here who's smoking 80 cigarettes per day is actually a very different person than this person over here who smokes 1 cigarette per day. But those people are different in a different way than smokers and non-smokers, right? I mean, to take an example, if you imagine that some people are prone genetically to become addicted to smoking if they try it, a person who never tries it, that potential addiction is kind of never activated, right? But a person who's smoking 1 cigarette per day is clearly somebody who's not smoking compulsively and is not under an intense compulsion, whereas the person out here with the 80 cigarettes per day perhaps has some uncontrollable behavior in relationship to smoking. So I'm trying to make this seem like you're actually getting 2 separate pieces of information. If you don't particularly like this example, there are plenty of other examples, and I have some that are more complicated in nature, but come from other studies that have the same mathematical structure. I mean, one of them had to do with a study of whether intensive treatment of ovarian cancer was more effective than sort of clinical trials style treatment of ovarian cancer. And that was had as a treated or control group, whether the oncologist was a gynecological oncologist or a medical oncologist. The gynecological oncologist treat using less chemotherapy than the medical oncologist. But most people aren't aware of the distinction, so they don't choose them in a particular way. An objection that was raised to that study was, so that created match pairs like these match pairs. Objection to that study that was raised was maybe the medical oncologists are better at measuring toxicity and other sorts of things that were being studied. And it's actually not an effect of giving more chemotherapy, but just how carefully they write it down. The medical oncologists are only writing down doing chemotherapy, whereas the gynecological oncologists are also doing surgery. But when you actually looked at this same analysis, the second piece, the dose-related analysis, if the gynecological oncologists had problems recording toxicity, they only had these problems recording toxicity when they didn't give a lot of chemotherapy. As soon as they gave a lot of chemotherapy, they suddenly became very good at recording toxicity, which sort of undermines that second argument. The mathematical structure is identical to this mathematical structure, but it's clearly a very different kind of piece of information. In terms of whether you should do one analysis or several, I think the question is whether you feel the kind of triangulation argument should resolve itself into one analysis where you don't see the pieces any longer, or whether it's better to see the pieces and see that you can survive with one piece without the other piece, regardless of which piece you set aside. So that's somewhat the difference between doing one big analysis and having two analyses which you combine. I imagine in most observational studies, we would have one main analysis, but do a couple of analyses to see it from a couple of angles. So we might do both types of analyses.
Thanks. I like the your example there of the oncologist and the oncologist, which is like a sort of physician preference IV. Yeah, that's nice.
Great. So thanks very much, Paul. That was lots of food for thought, and
Thanks for having me.
yeah, no, it's fantastic, and we'll be in touch.
Okay. Thanks for having me. Bye-bye.
Thanks so much. Bye.